Welcome to week 6 of pre-calculus. Our topics this week are inverse functions and exponential functions. So let's talk about inverse functions first. Remember the first week of the course, we talked about relations and functions. A relation, if you can recall, is a subset of the Cartesian product of two sets, x times y. Such a relation we call a relation from x to y. A function is a very special type of relation. It's a relation in which whenever you have pairs AB and AC in your relation, necessarily B equals C. In other words, you can have two pairs with the same first coordinate and different second coordinates. For every relation from a set X to a set Y, we can define the inverse relation. It will be from the set Y to set X. The definition is very simple. Whenever relation F contains an ordered pair X comma Y, its inverse relation G will contain a pair Y comma X. And in this case, we will write G equals F to the negative 1. Note immediately that this is not 1 divided by F. 1 divided by F doesn't make sense here because F is not a number, nor is it a function in general. It's a subset of the Cartesian product. Here is one example here. Say our set X is 0, 1, and set Y is negative 1, 2, 3. And the relation F is defined as pairs 1, 2, 1, 3, and 0, negative 1. Right? Clearly, it's a subset of the Cartesian product of X and Y. The entire Cartesian product of X and Y will have 6 elements. Right? In this case, X times Y will be the set containing pairs 0, negative 1, 0, 2, 0, 3, 1, negative 1, 1, 2, and 1, 3. My relation F contains only a subset of these, namely 1, 2, 1, 3, and 0, negative 1. Note, by the way, that my relation F in this example is not a function. Why is that? Well, this is because we do have two different pairs, 1, 2, 1, 3, that share the same first coordinate. And if you were to think of this as a function, you would have to assign to argument 1 two different values, 2 and 3. That makes F not a function. It is, however, possible to define the inverse relation F to the negative 1. All we need to do is take every pair in relation F and flip the coordinates in every pair. Right? So F to the negative 1 will be the set containing pairs negative 1, 0, 2, 1, 3, 1. Surprisingly, this new relation F to the negative 1 is a function, despite two pairs, 2, 1 and 3, 1, sharing the same second coordinate. Sharing the same second coordinate is perfectly fine. It simply means that the value of our function at 2 is 1, and the value of our function at 3 is 1. That's perfectly fine. So f inverse in this case is a function, even though f was not. In any case, f inverse is a relation. And note, by the way, that f to the negative 1 is a subset of y comma x. Excuse me, y times x, where again y is negative 1, 2, 3 times x, which is 0, 1. And this Cartesian product will also have 6 elements: negative 1, 0, negative 1, 1, negative 1, 1, negative, excuse me, 2, 0, 2, 1, 3, 0, and 3, 1. F inverse only contains negative 1, 0, 2, 1, and 3, 1. Once again, whether or not your relation f is or is not a function, it's always possible to define the inverse relation. If f is a relation from x to y, f inverse is a relation from y to x. Depending on the actual situation, f inverse may or may not be a function. In our example, f was not a function. However, the inverse relation was a function. It also should be clear that the inverse relation is always unique. Whether or not it is a function, it's always unique. When you flip all coordinates in every pair, you flip the first and second coordinates so that the second coordinate becomes the first coordinate and the first coordinate becomes the second coordinate. Naturally, the result is always unique. If, for instance, we were to flip coordinates in the relation f inverse, we would get 0, negative 1, 1, 2, and 1, 3, which is exactly relation f. So the inverse to f inverse is f itself. Here is a somewhat different definition specifically for an inverse function. We will see how this definition relates to what we talked before. Suppose now little f is a function from set x to set y. As we agreed in the first week, unless otherwise stated, sets x and y are always considered subsets of the set of real numbers. If there exists a function from y to x such that the composition of g and f leaves every element of the domain of f unchanged, we say that this function g is an inverse function of f. Two very important questions that arise here immediately are the following. Does every function have an inverse, just like every relation has an inverse? After all, a function is a very special type of relation. And if you view a function as a relation, of course, it will have an inverse relation. But will this inverse relation be a function too? That is a question. Does every function have an inverse function? Is the first question, and the second question is it unique? Again, this question is not relevant for relations and their inverses as defined here, because when you flip coordinates, the result is always unique. But in the sense of this definition, it may be an interesting question. We'll suppose this function g exists. Does it have to be unique? Or there could exist multiple functions g with this property? If an inverse exists, does it have to be unique? Well, to study these two questions, let's go over the following discussion. Suppose an inverse exists. An inverse. We don't yet know that it is unique. Suppose a function g with this property exists. Then I claim that function f must have a very special property. It must be that for every elements x1 and x2 of the domain, whenever the value of f at these 2 points is the same, the 2 points are the same. In other words, let me draw a picture that explains why this property holds. Whenever a function g from y to x with the property that g of f of x equals x for all x in the domain of f exists, the function f must have the following property. For every elements x1 and x2 of the domain of f, we have the implication that whenever f takes the same value at these 2 points, it follows immediately that the 2 points are the same. In other words, our function f takes different values at different points. It cannot take the same value at two different points. Why is that the case? Let's draw a picture. This potato is the domain of f, which is x. This is the codomain y. Let's say this is A, let's say this is B, and f maps A to B, which means f at A equals B. If our function did not have that property, we would have potentially another point C, which f maps to B. With A not being the same as C. But how would that function G look like? Well, the function G must have this property, that G of f of x must be x for every x. All right, so it means immediately that G at B must be simultaneously A and C, right? Because B here is f at A. On the one hand, B is f at A. And so by our requirement, GF at f at x is x. So G at f at A must be A. On the other hand, I can write B as f at C. And by the same requirement, GF at f at x must be x. We have that G at f at C must be C. And we come to a contradiction. We come to the conclusion that A equals C, but that's not true. So a situation like this can never occur for a function f that has an inverse. A situation like the one above cannot occur for a function f that has an inverse. Or equivalently, if a situation like this occurs, f has no inverse. Again, if it's known that f has an inverse, necessarily f has this property. It cannot take the same value at two different points. This condition is necessary for a function to have an inverse. If this condition is not met, our function has no inverse. Functions like this have a special name. They're called injective or one-to-one. And again, a function from x to y is called injective if different x's go to different y's. Or another way to say it, that if it's known that the y's are equal, then the corresponding x's must be equal. Graphically, it means our function passes the horizontal line test. Which says that the function is injective if and only if any horizontal line in the xy plane intersects with the graph at most once. The graph in the picture corresponds to a function that is not injective because we can clearly see that we have distinct points x1 and x2, yet the value of f at these 2 points is the same. Once again, for a function to have an inverse, it's necessary that the function be injective. There must be no gluing, like in this picture. A and C glued to B upon the action of F. This must not occur in order for a function to have an inverse. That more or less answers the first question. Does every function have an inverse function? No. If a function is not injective, it has no inverse. A function whose graph you see in the picture, for example, has no inverse. If you were to write this function as a relation, as a set of ordered pairs, it would, for instance, have pairs x comma y, where y is the value of f at that point x1, and the pair x2 comma y. That is because f at x1 equals f at x2 equals y. If you were to flip the coordinates in this relation and write f inverse as a relation, it would of course exist. It would be the set of pairs in which we simply flip all coordinates. So instead of x1 comma y, we have y comma x1. And likewise, instead of x2 comma y, we have y comma x2. But now we see immediately this is not a function because we have 2 pairs sharing the same first coordinate but different second coordinates. This relation is not a function. In other words, f as a function has no inverse function. F as a relation does have an inverse relation. So we have the first question answered. Now what about the second question? If an inverse exists, does it have to be unique? The answer is no. When an inverse exists, it is generally not unique. And here is an explanation why. Consider a function f from x to y with the following property. With the property that the image of function f is a proper subset, so it's strictly smaller than the codomain y. This red circle, for instance, is the image of f. It lies entirely inside the set y, but it's less, strictly less than the set y. And suppose that the necessary condition for f to have an inverse is met, so f is injective. Let me move this to a new page. Suppose that f is injective. Then I can define many different, at least two in fact, functions g that satisfy that definition. I can define multiple functions g such that g of f of x equals x for every x in the domain of f. How? Well, I could define, let's call it g, from y to x via the following formula. I'll say g of y. G of y is x if y is in the image of f and f at x equals y. Know that this makes sense because there will be unique x with that property. There will be exactly one x with this property. There will be one because y is taken from the image, so element y must be the image of f, must be the image of x under the action of f for some x. That's what it means to be in the image. It means that you are equal f at x for some x. Why can't there be another x with this property? Because then the function f wouldn't be injective. If there was, say, x1 with the property that f at x1 also equals y, it would violate the assumption that f is injective. So there is one and only one x in x with this property. So far, there is no freedom. It's not clear as to why this function g would not be unique. But something interesting happens when my value y lies outside the image of f. What if y is here? So y doesn't correspond to anything in x. I can assign the value of g at y to be pretty much anything else, to be pretty much anything. I could, for instance, take the smiley face. And yes, instead of the smiley face, I could take anything. Let me just say anything. And because the image of f is less than y, I have this freedom to assign the value of g at y to be anything I want. We can take a specific numerical example. Let's say f is defined on the set 0 infinity to the set of real numbers as square root of x. X gets mapped to square root of x. What is the image of f in this case? The image of f in this case is clearly the set of all non-negative real numbers, which is not the entire set of real numbers. Right? It's strictly less than R. It's a proper subset. So I claim we will be able to find more than one inverse function g in this case. For example, I could define function g for any y in the set of real numbers. I could define g at y to be, well, if y is in the range, if y is non-negative. I could define g at y to be y squared, and it has to be y squared. That's if y is non-negative. Why is that? Well, after all, I want g at f at x to be x. In my situation, g at f at x will be G at f at x is root x, and g at root x, because root x is always non-negative, will be root x squared. That's x. But what if y was negative? What if y was negative? Negative numbers are not in the range of f. I could then define g at such a point y to be pretty much anything. And I would still satisfy this property. For instance, I could say that if this number anything is, say, for instance, 0, I could put g at negative 1 to be 0. And I would still satisfy this, g at f at x equals x, for every x in the domain of f. Let's put 0 specifically. Or I could have another function, g1 at y, which is also y squared if y is non-negative. And here, instead of 0, let's say 1, if y is less than 0. Clearly, functions g and g1 are not equal. Both g and g1 are functions from the set of real numbers R to the set of non-negative real numbers. But they're not equal. But they're different, distinct. Both could be called inverses of our function f. Both g and g1 qualify as an inverse of f. The reason why we have this freedom in having multiple inverses is precisely because the image of the function f is not the entire codomain y. I have these values. I have elements of y outside the image of f. When I think about what g at these points should be, I have this freedom. I would have no such freedom if the image of f was all of y, though. That's very important. That trick, of course, wouldn't work if I didn't have any elements of the codomain y outside the image of f. That brings us to an important definition. These functions whose images are equal to their codomains are called surjective. If the image or range of f is the entire codomain, the function f is called surjective. And a necessary condition for uniqueness of an inverse is that the function be surjective. In this example, our function f from 0 infinity to r is not surjective. That is why the inverse is an inverse was not unique. This is why it has multiple inverses. If the image of f, this red circle, was the entire codomain y, I wouldn't have this line here at all, and the inverse would be defined uniquely. So we have this theorem. For a function f from x to y to have a unique inverse, it is necessary and sufficient that f satisfy two simple conditions. First, that f is injective, and second, that f is surjective. In other words, that the image of f be the entire codomain. Functions that are both injective and surjective are called bijective. So I can restate this theorem in the following way. For a function to have a unique inverse, or the unique inverse, I should say, it is necessary and sufficient that the function be bijective. Of course, this unique inverse will be denoted by f to the negative 1, or sometimes pronounced inverse f. I should warn you immediately that inverse is not the same as reciprocal. F to the negative 1 is not literally f raised to the power negative 1. So it's not the same as 1 divided by f. Although occasionally this might be the case. It's interesting to think about what functions, if any, have this property. Are there any functions whose reciprocal equals their inverse? In general, that's certainly not the case. Do not confuse these two concepts, reciprocal and inverse. Here are some simple numerical examples. In this example, we know that f at 2 equals 4 and f at 5 equals 12. What are the corresponding input and output values for the inverse function? Well, the fact that f at 2 equals 4 and it's known that f has an inverse function, we know that f inverse at 4 equals 2. f moves 2 to 4, which means that f inverse moves 4 to 2. And likewise, f at 5 equals 12, it means that f inverse at 12 equals 5. So f moves 5 to 12, so f inverse moves 12 to 5. Example 3. F here is 1 over x plus 2 and g is 1 over x minus 2. The question is asking, is g an inverse of the inverse of f? Let us work on this on a separate page. For neither of the two functions are we given its domain explicitly, and by our old-time convention, we assume that both functions are defined whenever their formulas make sense. So in particular, function f is defined for all those real x for which x plus 2 is not 0 because x plus 2 is the denominator. That is a union of two intervals from negative infinity to negative 2 and from negative 2 to infinity. Or you can write this as r minus the set containing 2. What about the graph of this function? Can we apply the horizontal line test? How does the graph of this function look like? We know 1 over x is a parabola shifted. 1 over x, is a hyperbola. So 1 over x plus 2 is a hyperbola. 1 over x shifted 2 units to the left. X equals negative 2 is a vertical asymptote. And y equals 0 is a horizontal asymptote. The value at 0 is 1/2. And we see immediately that the function does pass the horizontal line test. There is no line that intersects with the graph of this function more than once. The function f passes the horizontal line test, as there is no line that passes, or rather intersects, the graph of f more than once. What about the image of f, by the way? Well, if we were to equate 1 over x plus 2 to some y, and think for what y's would this equation have a solution, excuse me, if we equate 1 over x plus 2 to y, the question is, for what values of y would this equation have a solution for x? Well, if we solve this for x, we're multiplying by x plus 2. Which is, of course, not 0. And here we get x plus 2 times y equals 1. And so to solve this for x, we must have y not 0. And if y is not 0, x is simply negative 2 plus 1 over y. This answers the question about the image. Image is all the y's in the real line, on the real line except 0. For any such non-zero y, we can find a solution of this equation in x. X is negative 2 plus 1 over y. So if we view function f as a function from r minus 2 to r minus 0, we conclude that f is both injective and surjective. And so it has a unique inverse. All we need to do now is check that G composed with f is the identity map, identity function on the domain of f, which is r minus 2, i.e., we check that G of f of x equals x for every x in R except 2. So g of f of x in our situation is g of 1 over x plus 2. What does g do to its argument? It takes the reciprocal and then subtracts 2. So, of course, it will be x as expected. So g is the inverse, the unique inverse of f. How about the other example here? X cubed and 1/3 x. Well, the function x cubed is bijective. That's what we immediately see. Even when viewed from R to R, that is because x cubed is both injective, it's monotone increasing, and surjective for every fixed y. I can find an x whose image under the action of f is y, that x is cubic root of y, right? F at cubic root of y will be cubic root of y to the power 3, and that's y. So because f is bijective, it follows that f has a unique inverse. The question is it G? To verify whether G is the inverse of f. We must verify that G of f of x equals x for every x in the domain of f, which is the entire real line. Now, what is G of f of x? F of x is x cubed, and what G does to its argument, it divides it by 3. So G of f of x is x cubed. That's not x. It's definitely not x for all real x's. It could be x when x is 0. But for instance, when x is 1, that's not true. 1/3 x cubed equals x is false when, say, x is 1. So the answer is that G is not the inverse of f. A natural question arises here. If given function G is not the inverse of f, what is? Well, we claim that the inverse of f is cubic root of x, which is, by the way, also defined on the entire real line. Cubic root is defined for all real numbers. And that's really easy to check. Let's call cubic root of x some h. I claim that h is inverse of f. Well, h composed with f is f is x cubed, and we get cubic root of x cubed. Well, cubic root of x cubed equals x for any x, positive, negative, or 0. And that shows that h is indeed the unique inverse of the function f. And this last problem of this type was when f was x minus 1 cubed. Note that f is defined on the entire real line, and the image is also the entire real line, just like in the previous problem. For x cubed, the domain and image are both the entire real line. So here also, domain and the image is the entire real line. That's easy to see when you draw the graph. This, after all, is simply the cubic parabola shifted 1 unit to the right. And let me redraw it. Like this. Function g in this example was cubic root of x plus 1. And again, the question is if g is f inverse. Well, because g is clearly injective, passes the horizontal line test, and it's surjective. The image is the entire real line. Codomain equals image. So it has a unique inverse. Now the question is it G? Well, we simply need to check whether G composed with f of x equals x. G composed with f at x is G of f at x. F is x minus 1 cube. And what G does to its argument, it takes cubic root of the argument, then adds a 1. Cubic root of x minus 1 cube is x minus 1. When you add 1, you get x. That is for every x in the set of real numbers. All right, let's have a break here. Thank you.